Hello everyone. We're going to start working through another example here. We have another divide and conquer recurrence, and we've made this one worse in several ways. So this is going to be getting towards the upper end of difficulty we can see for these problems. So let's start just going through the details and seeing what happens. We have to plug whatever appears inside of t on the right-hand side, which is n over 4, into the equation, which I've designated with a red bar. Let's do that. The left-hand side, we get t of n over 4 is equal to 3 times t of n over 4, which is n over 16, plus c, careful plugging in here, we have n squared, so we do that as n over 4 squared. Now let's replace the t of n over 4 with the right-hand side here, underlined in red. So let's make that substitution. We get t of n equals, we have a 3 times my right-hand side there, 3t of n over 4. Not n over 4, n over 16, be careful. Plus c times n over 4 squared, plus cn squared. Let's distribute the 3, and we get t of n equals 9 t of n over 16 plus 3c times n over 4 squared plus cn squared. And those terms at the end don't look like they're going to combine in a nice way, so I'm not going to combine them yet. So let's continue with our substitutions. We're going to plug n over 16 back into the original equation. So plug n over 16 into the red barred equation. Making that substitution, the left-hand side would become t of n over 16 is equal to 3 times t of n over 16 over 4, which is n over 64, plus c n squared, but n is now n over 16, so it's c n over 16 squared. Now substitute this right-hand side, underlined in light blue, with t of n over 16. Making that substitution, we have t of n equals 9 times this right-hand side here, 3t of n over 64, plus c times n over 16 squared, plus the other stuff we still had from the original equation, which is 3c times n over 4 squared plus 3cn squared. Let's distribute the 9 and see if anything nice happens. We have t of n equals 9 times 3 is 27 times t of n over 64 plus 9c times n over 16 quantity squared plus 3c times 9 over 4 quantity squared plus cn squared. This is looking real messy, but thankfully there's some nice things happening. Let's look at the t term. We have a coefficient of 27, and a coefficient of 9, and a coefficient of 3. That looks like powers of 3. So we have 3 to the k. And the stuff inside of t is n over 64, n over 16, n over 4. That's like n over powers of 4. Both of those things aren't too surprising. The coefficients out front are coming from distributing the 3 over and over and over again. And the thing inside of the t comes from continually plugging into n over 4, n over 4, and n over 4. So none of that's that surprising. How about over here? Let's try and write this as a summation, as we typically do. A sum from I equals 0 to k minus 1. What do the terms look like? Well, we have a 9, a 3, and a 1 out front. Those look like powers of 3. So we have 3 to the I times c times the stuff inside of the squared is n over 16, n over 4, and n. That looks like n over powers of 4 squared. So those are two terms. So for any value of k, we have t of n equals 3 to the k, t of n over 4 to the k, plus the sum from I equals 0 to k minus 1 of, we'll write it in the same way. 3I times c times n over 4 to the I quantity squared. Now, just like we've done every other time, we want to find out when does this stop. It stops when our thing inside of t, which in this case is n over 4 to the k, is equal to our base case. So let's scroll up. What's our base case? We have a typo. Should have been t of 1 equals c. So we want to set this equal to 1. Let's solve that for k. Skipping a bit of the algebra, that's k equals log base 4 of n. Let's substitute that into our expression now. We have d of n equals 3 to the log base 4 of n times t of n over 4 to the k is just t of 1. I knew that was going to happen on purpose. Plus the sum from I equals 0 to k minus 1. Maybe we do a bit of work with the summation, so maybe we pull out the c and keep the 3 to the I in there, and maybe even square that fraction. So we can write that as n squared over 16 to the I. One nice thing happens here, which is t of 1 is just a constant. But we need to analyze that summation. So let's go and do that. We have to analyze the summation from I equals 0 to k minus 1. Let's even write it in a bit of a nicer way as n squared times 3 to the I over 16 to the I. So, to do that, maybe we start by pulling the n squared out of the summation and write it as 3 to the I over 16 to the I. And now, if we remember, these summations are typically easiest to analyze by bounding. So we're going to bound above. To bound it above, we can write it as an infinite summation. That definitely makes it bigger. And I can write the inside as 3 over 16 to the I. And maybe somewhere to the side we say, hey, recall that the sum from I equals 0 to infinity of r to the I is 1 over 1 minus r. So let's use that fact. This is equal to n squared times 1 over 1 minus 3 over 16, which it doesn't really matter what that constant is, but let's find it all the same. N squared, 1 over 1 minus, let's actually do the arithmetic. It's going to be 13/16. So this equals 16 n squared over 13. So it's bounded above by a constant times n squared, so it's in big O of n squared. Let's also bound it below. Bound below. This is where we get to make lots of savings. The purple summation there is definitely bigger than or equal to replacing the entire summation with the first term, which is just 1. And hey, look, that's in big omega of n squared. It's in big O of n squared, and it's in big omega of n squared. So the original summation from I equals 0 to k minus 1 of n squared times 3 to the I over 16 to the I is in theta of n squared. Now we can take the summation that's appearing inside of my recurrence up here and replace it with theta of n squared. So let's do that. We have, so t of n is equal to 3 to the log base 4 of n times c plus c times theta of n squared. So maybe I just write all of that as theta n squared. Now, which thing wins here? This first term, I can't really analyze it as it's written, so let's try something. If you recall, there's an algebraic trick that we mentioned earlier in the class, which was x to the log base a of b is equal to b to the log base a of x. We can swap the two things there. So this first term I can rewrite as n to the log base 4 of 3 times c plus theta n squared. Now we need to determine which one is bigger, n to the log base 4 of 3 or theta of n squared. This might not be obvious at first, but if we look at log base 4 of 3, log base 4 of 3 is definitely less than 1. Why is it less than 1? Well, I know that log base 4 of 4 is 1. So that thing in the start there is less than 1 for a power, which means that's less than n. So we're comparing something less than n to something like n squared. The winner there is definitely n squared. Since that's true, t of n is in theta of n squared. Depending on the problem, it's actually possible that the first term could have been the dominant term. So we can't always just ignore the thing that's appearing out front there. This problem is noticeably harder than some of the ones we've seen in the past for various reasons. First, the substitutions are just messy because the numbers are bad. Second, the pattern noticing here is tough, so you might need to be careful there. And then analyzing the summation is very non-trivial as well. So this is a very involved problem. But like I said, this is on the upper edges of the difficulty of things I'm going to expect from you guys going forward. But that is how we would analyze a problem like this. And it's not much different than what we've done before. It just involves a couple more algebraic steps along the way.